We'll just wait for a few more minutes and then we'll start. Let's begin. Hello everyone, I'm Tanya. I'm one of the TAs assigned to the aircraft design course taught by Professor A.K. Ghosh. So today we'll go over the questions of week 3. Before that, we had left a few questions from last week, so we'll just start with that. Yes, so uh, when the angle of attack decreases, the moment of center of pressure will be. So I believe that I had asked all of you to try getting this answer. Have you tried to solve this? Towards the leading edge. Okay. Can you try to explain that? You said D, right? So Deep Tanu, I hope I'm pronouncing your name right. Can you try to explain why you said it's all of these? How can it be all of these? How can it move towards the trailing edge, leading edge, and be independent of angle of attack? Can you try explaining your answer? Or does anybody else have a different answer and try to explain it? Am I audible? Can someone confirm if I'm audible? Yeah, okay. So can one of you try and tell me the answer of this question and try to justify it? What's the trailing edge? Can you tell me why? Why did you say it's towards the trailing edge, Prajwal? Maybe due to pressure distribution. Okay, can you explain it further? Like, how does the pressure distribution change? And Harish has said C. Can you explain your answer? Just with the concepts that we already know, just try to answer it. So yes, it is obviously due to the pressure distribution, but what changes in the pressure distribution makes it move towards trailing or leading edge? Okay, Harish, you said C. Can you try explaining your answer? C is towards leading edge. Can you? Yes. Since the CG will go towards, okay. What was the message? Okay, since the CG will go towards the leading edge, when angle of attack decreases, CP would also react in the same manner. Does the CG move when the angle of attack changes? What is CG? What is CG? Center of gravity. Does the center of gravity change with angle of attack? It's fixed, right? So, Harish, your uh, not Harish, sorry. Yes, Harish, your answer that says that the CG goes towards leading edge when angle of attack decreases, it's problematic because CG does not change with respect to angle of attack. It's fixed, right? So it's the distribution of mass. The mass distribution gives you the CG, which is fixed. It will not change with respect to angle of attack. So that is not the right explanation. So you said leading edge differentiates the pressure difference and angle of attack creates lift. I'm not sure how that justifies it. Leading edge differentiates the pressure difference. And the angle of attack creates lift. The angle of attack has always created lift, right? So if I decrease the angle of attack, why do you say that the center of pressure will move towards the trailing edge? The rest of you also please contribute. Okay, do one thing. All of you just try to Google it and find out the answer. I had asked you to check this up last week. Just try it now while we are in this session. Just try. Just go to Google and see how a center of pressure varies with angle of attack. And then try and tell me. Yes, it is related to the pressure distribution, but what changes in pressure distribution gives you the moment of CP towards leading or trailing edge? So it is not independent of angle of attack. That is false, right? Because the point that is independent of angle of attack is, what is the point that is independent of angle of attack? What is this point? Okay, Harish, I think you should start messaging to everyone so everybody can respond. No, CG is fixed with respect to it has no point, I mean, it has no relation with angle of attack. So I don't think it comes into play here. It's nothing to do with the aerodynamics. Okay, CG is just with respect to mass distribution. So something, some aerodynamic parameter. What is the point that is independent of angle of attack? With respect to aircraft stability, aircraft performance, AC, yes, aerodynamic center. So aerodynamic center is the point that is independent of angle of attack, which is why and CP is not a point that's independent. So it is not option B, and it's certainly not option D. So it's one of the other two. So just try Googling it and tell me the reason, which is the right answer and why is it so? Does it take so long to come up with this answer? Please just Google it and tell me. So the right answer is trailing edge, right? Towards trailing edge is the right answer. Can you tell me now? Give me a justification, some reasoning as to why it moves towards the trailing edge. Nothing? Can someone tell me some answer? Something that you found on Google? Okay, I don't think that there's any point wasting time on this question. Again, please go home, go after this and try getting the answer of this. Okay, someone's replied. When the aerodynamic center is steadily increased towards the positive angle of attack, the lift component grows rapidly up to a point before abruptly dropping off. The drag component of this moment increases slowly at first and rapidly as lift decreases. Yes, but why does this cause the center of pressure to change? What you've written is true, right? So when what he has said is that when the angle of attack increases, it lift also increases steadily until a point. What is that point? That is stall. So your lift curve is this. So when the angle of attack increases, the lift increases steadily until this point, which is your CL max or alpha stall, right? That is true. But why does this relate to center of pressure? Okay, let me know when you find the answer to this or find the We know the answer. Answer is it moves towards trailing edge. If somebody finds a reasoning for it, do let me know, but we'll move on to the question after this. The explanation, I'll give you once one of you give me one justification, right? So we'll get to this if one of you comes up with a justification. Yeah, so this is another question. For airfoil NACA 633018, what is the location of minimum pressure from leading edge? We had briefly gone over the NACA series, 4 series, 5 series, 6 series. This is part of the 6 series. So which of these digits or pairs of digits gives you minimum pressure? Okay, sorry about that. I think there was some technical issue with the Zoom link. I'll just start sharing again. I'm sorry, but there seems to be some issue with the link on my systems. Just give me a second. Am I audible? Yes, okay. So just give me a minute to log into the tablet. Okay, so I hope the screen is visible now. Yes, and please refrain from sending direct messages. Just put it up on the for everyone to view. Okay, so yeah, where were we? Yeah, what was the location of minimum pressure for a NACA 6 series airfoil? Does anyone remember? Just go to that. I think it's going to take a few minutes for the slide. Yeah, so from this, can you try and tell me what is the location of minimum pressure? What is the location of minimum pressure? 0.3 C, exactly. So 0.3 C. Okay, next. Yeah. For an airfoil, the same airfoil, what is the location, what is the maximum thickness to chord ratio? %18%. So it's 0.18. The ratio is 0.18, correct. Okay. For an aircraft to fly, okay, it hasn't loaded. Yeah. For an aircraft to fly at design CL.6, which is the most suitable airfoil? So for your NACA 5 series and 6 series, just try to recall what was the digits that correspond to design CL and see which of these airfoils give you the most suitable CL, that is 0.6. C, that is third option. Okay. So these are, just give it a few seconds. Yeah. So these were the examples that we had considered while looking at the NACA 5 series and 6 series. So just see what is the location of design lift coefficient. So the first digit for the NACA 5 series, the first digit when multiplied by 1.5 gives you the design lift coefficient. For the NACA 6 series, the third digit is this one. So in these cases, it's this one. So that digit gives you the design lift coefficient in 1/10th. Okay. So for 0.6, it is the third option. He's right. Okay. So let's just go to the next question. So these are the questions from so week 3 assignment. Yeah. A symmetrical airfoil has, we've gone over this multiple times, let's go over it quickly. Symmetrical airfoil has what type of camber? No camber, correct, zero camber. A positively cambered has a positive camber. Very simple. Yeah. Which of the following is correct? Assume the conditions are the same. Drag by sphere is less than produced by airfoil, equal to produced by airfoil, greater than produced by airfoil. Tell me the answer and the reasoning. So this question is given and the solution is given, but can you tell me the reason why the drag produced by sphere is more than drag produced by airfoil? Yes, C is the right answer. Can you give me the reason why? Flow separated at the end, correctly. So flow separates even for an airfoil, but and not until very late, but for a sphere, it separates earlier. So this gives you the comparison of a flat plate or a disc, a sphere, and an airfoil. So the flow separates in all three cases, but for an airfoil, it's only towards the trailing edge, towards the very end. So till then it produces, it's like there is a boundary layer, which gives you the pressure distribution and which in turn gives you the lift. But for a sphere, the flow separation happens almost immediately after the leading edge. And it's the most, like the drag is the most for the case of a flat plate, the first one. Okay, so the vortices occur very soon, and so the flow is separated very soon. Okay. Next, for the airfoil NACA 0012, what does 12 signify? Again, very simple. Thickness of the airfoil, right? We've gone over this multiple times. Almost all the series, the last two digits correspond to the thickness. Okay. The aircraft has a gross weight of 1,700 kgs. At the end of the mission segment, it has a weight fraction of 0.9. Determine the fuel consumed during the mission. We've done many such questions. So can you quickly tell me what is the answer and what formula should we use? So they've asked you fuel consumed. Initial weight is W naught. W naught minus final weight by W naught gives you the fuel fraction. Weight of fuel by W naught, correct? So W naught is something that we have. It's the initial weight. So let's just simplify this. You get W1 minus W1 by W naught is weight of fuel, W naught, and this weight fraction is given to you, right? So after the mission segment, what is the weight fraction? That is 0.9. It gives you weight of fuel by 1,700. Therefore, weight of fuel is, what is the answer? 0.1 into 1,700, 170, right? 170 kgs. Okay. Next question. An airliner with a takeoff gross weight of 2,100 kgs is cruising with a fuel weight fraction of 0.28. Then what will be the weight of fuel? Similar to the previous question, but the quantity given to you is different. So how do you proceed? What is given to you? They're giving you fuel weight fraction. So fuel by W naught is given to you as 0.28. They've directly given the fuel fraction and they've asked you to find out weight of fuel. So it's just 0.28 into W naught, which is 2,100. What is this value? So the solutions are given to you. It is 588 kgs. So it's there in the solutions, direct formula. The aspect ratio of a square wing is, what is the formula for aspect ratio? What's the formula for aspect ratio? B square by S. Very good. So B square by S. And so for a square wing, the area, so this is B into B, and the area of a square wing is nothing but the span into chord. So which gives you span into chord. So it's a square wing, so it will just be B into B, right? So it's 1. Correct? The span and the chord would be the same dimension. So yeah, so it's equal to 1. Next, what is the effect of increasing the camber of an airfoil? Very straightforward question. What is the answer? Increase the camber? Yes, it increases the lift. Correct. Increases the lift. Doesn't say much about the drag, okay? So it does have an effect on drag, but we increase the camber to increase the lift. Okay, and it doesn't really reduce the drag. Okay. A high performance glider has a maximum lift coefficient CL max of 1.6, wing area of 18 meters square, density ratio 0.495, weight of 1,200 kgs, calculate stall speed. We've done stall speed multiple times. So what was the formula? Under root 2W by S rho CL max, right? So it's 2 into W is 1,200 into 9.81. S, how much was S? 18. Density, they've given you density ratio. They've given you this, right? So that is nothing but density by density at sea level. So density is 0.495 into density at sea level is 1.225. So put that here. 1.225 into CL max is 1.6. What is the answer? Okay, so 36.72. It's 36.717 meters per second. So 36.72. Okay, next question. For high aspect ratio wing, this question somebody had brought up on the forum. So let's just ignore this high aspect ratio, okay? Just ignore that. For a wing at low speed, the relationship between the lift curve slope of the wing and the airfoil is given below. Okay, so they're giving you 3 relations. Which of the following is correct? Which is the right answer? So the ratio, the relation for CL alpha 3D, which is the wing, and CL alpha 2D, which is CL alpha of airfoil, is CL alpha 2D by 1 plus CL alpha 2D by pi EAR. So which of the following is the right answer? A, B, C, A and B, or all A, B, C? B, all A, B, C. Why are all of them correct? So this is a direct formula, what we've written there. For an elliptical wing, E. What is E in this formula? What is the small e? What is that small e? Oswald's ratio, yes. So it's the span efficiency factor, which is equal to 1 for elliptical. Okay, so which is why there's e absent here. So this is right, this is right. And for a square wing, aspect ratio is 1. We just came up with that. So that's why aspect ratio is absent there. So all three are right. Okay, let's go. So in the last class, we had seen that one of the benefits of high wing was that it provides greater lateral stability. Can you try and tell me some other benefits of high wing? I just thought we should go over this before we move into week 4 contents. One was better lateral stability, right? Lateral stability. Can you try and tell me some other benefits? Structurally, can you just think about it? High ground clearance, yes. So that is the first point. Large ground clearance. Great. So that means that the fuselage is lower, and so it's easier to do the maintenance. That is, in fact, one of the points. So there's larger ground clearance, the fuselage is lower, which makes it easier for maintenance. Any other points? So there's less probability of wingtips hitting the ground during takeoff. Yes, something along similar lines. So the next is the fuselage is closer to ground, better for maintenance. Another point is that you have additional structures to support the wing. So you have, when there's a high wing, you can have other structures that support the wing. So then you can relieve it of its loads, right? So you have additional structures to support the wing. That's one reason. And another thing is that enough clearance for maximum flap deflection. So during takeoff, you can deflect your flap, the maximum you can deflect. So if your wing is low, if it's a low wing configuration, there is a limit to how much you can deflect your flap. That is not true for the case of high wing. Okay, I just thought we should go over these conditions before getting into week 4 contents. Okay, so for an incompressible flow, if local area velocity decreases, the dynamic pressure will decrease. Yes, so dynamic pressure is Q is nothing but half rho V square, right? So if this V decreases, then dynamic pressure will also decrease. Correct. What is the thickness of NACA 0002 airfoil? So for a 4 series, the last 2 digits signified thickness to chord ratio. 2%, correct. So it's 0.02 in hundredths of chord. That's nothing but 2%. Correct. Yeah, so this is just what we had seen. What is generally given in a swept back wing to avoid tip stall? So you understand what a sweep back is, right? So if this is your fuselage and the wing has a sweep angle. Okay. So this is the sweep angle. So for a swept back wing, what is generally given at the wing tip to avoid stall? So it cannot be flaps. Flaps are not used for avoiding wingtip stalls. It's a high lift generating washout. Can you tell me what washout is? You said it's washout. Washout is the right answer. Can you tell me what washout is and why is it given? How does it avoid tip stall? Geometric twist, angle of attack. Yes, so, okay, let's just try to understand this. So the angle of attack at the root is greater than the angle of attack at the tip. How does this avoid tip stall? So that is what washout is a characteristic of aircraft wing design, which deliberately reduces the lift distribution across the span of an aircraft's wing. Yes, the characteristic is that there's a geometric twist, right? So geometric twist, what does it say? That the angle of attack at the root is much higher than the angle of attack at the tip. So there is a twist introduced into the wing. How does this avoid a tip stall? So if your root is at an angle of attack, yes, root will stall first, correct. So if your root has crossed alpha stall, since there is a reduction or there's a twist towards the tip, downward twist towards the tip, the angle of attack at the tip will be much less than alpha stall. Not much less, but still lesser than the alpha stall. So even though the root cannot produce the desired lift, across the span of the aircraft, span of the wing, it will produce some lift for some more range of angle of attacks. Okay, so progressively towards the tip, you will have alpha less. Alpha will be less than alpha stall. So let me try to explain this. Yeah. So this is how they've introduced this wing tip geometric twist towards the wing tip. So oops. So the root is at some positive angle of attack. So it is in fact placed at a higher angle of attack. So here it says 1.5 degree. So it is set, this wing setting angle is at 1.5 degree. But the wing tip will be at a negative angle. So towards the tip, it has a twist. Okay. So even when the wing root experiences alpha stall, the wing tip will not have an angle of attack that is greater than alpha stall. Okay. Okay. Let's go to the next question. We've done this multiple times. What is a reflex cambered airfoil? It's a camber line that curves back up near the trailing edge, right? And what is the use of this? What is the use of a reflexed cambered airfoil? Why did we have to come up with this reflex cambered airfoil? We've discussed this several times. Why do we need a reflex cambered airfoil? Okay, what is a Thales aircraft and how is it useful there? What property of the reflex cambered airfoil is desirable to us? Tailless aircraft. Yes, it's useful in tailless aircraft, but what property? Why is it useful in tailless aircraft? So for a symmetric airfoil, the moment at the aerodynamic center, Cm0 is 0. For a positively cambered airfoil, the moment at the aerodynamic center, Cm0 is less than 0. What happens when Cm0 is less than 0? This was your Cm versus alpha graph. So this is it. And if your Cm0 is less than 0, it looks like this. what happens is that it will trim at a negative angle of attack, which is not something that we desire. We want to trim the aircraft at positive angles of attack, like this. Okay, so if we use a positively cambered airfoil, your Cm naught is less than 0, and we will have to trim the aircraft at negative angles of attack. To avoid this, they introduced the reflexed cambered airfoil, which is something like this. So there's an upward camber towards the trailing edge. What happens is that your Cm naught becomes either 0 or greater than 0, right? So then you can trim your aircraft at 0 or positive angles of attack, which is a desirable trait. It's not mandatory, but it's desirable. It's not mandatory in terms of stability. Okay. Yeah, so these are the different types of airfoil that we've seen in the last class. This is the reflex airfoil, reflex cambered. So there's a slight upward curvature towards the trailing edge. Okay. Okay, determine the corrections or otherwise of the following assertions and reason. So read the two statements. Assertion says most of the wings use cambered airfoils, and the reason says cambered airfoils can produce positive lift at 0 angle of attack. Is the first statement true? Most of the wings use cambered airfoils. Is it true? Is the assertion true? First statement, is it true? Is the first statement true? Most of the wings use reverse cambered airfoils. It is true, right? So it produces more lift, and so we use the cambered airfoils, which is what we have been discussing throughout this course. So yes, the first statement is true. Second statement, cambered airfoils can produce lift at 0 angle of attack. Is this true? Is the second statement true? Yes. And is the second statement the reason for the first statement? Yes. So the correct answer is both A and R are true, and R is the correct reason for A. Okay. Next question. For a cambered airfoil, Cm naught AC is. We just discussed this. What is the right answer? We just discussed this. When it says cambered, it means positively cambered. B. Yes, always negative. And why is it always negative? Yes, less than 0. But why is it always negative? From where does the Cm naught come? That is the Cm at 0 angle of attack. From where does it come? Moment at HC is less than 0. Yes, but why is it less than 0? For a cambered airfoil, why is it less than 0? We've discussed even this several times. So we just saw for the cambered airfoil, it is 0, right? For symmetric airfoil, it is Cm naught is 0. For a positively cambered airfoil, Cm naught is less than 0. Why? Even this we have discussed multiple times, so please answer. We've discussed this a lot of times. Can you just try to find out why it is? Just try. If not, please Google it and tell me right now because this we have discussed multiple times. Why is the CM naught for a cambered airfoil less than 0? Why is the CM naught for a symmetric airfoil equal to 0? We even discussed how the reflexed airfoil manages to make it 0 or greater than 0, right? So at that time, we had discussed this extensively. Please take a few minutes and try to tell me this. Google it or go back to your notes or something and do tell me the reason why is it negative. Have you got the answer? Can one of you at least try to give me a reason? Please just take a couple of minutes, refresh your notes, go through the notes, or Google it and let me know. Have you gotten the answer? Okay, I'm not going to give you the answer, but we'll discuss this in the next week. Please do find out at least by then. Next question. Wing aspect ratio is defined as, we just went over this. Moment tends to pitch down. Yeah, why does it tend to pitch down? Please just find out the reason for this. So I'm guessing the answer was for this, but yes, it tends to pitch down. So that is why you're CM not, I mean, that means that moment at AC is less than 0 means that it tends to pitch down. But why? Why is it? Either go watch the previous videos or Google it and let me know in the next class. Okay, going back. Wing aspect ratio is defined as span square divided by reference area, right? So we've done this multiple times, so it's just b squared by s. Okay. What do winglets do? Increase thrust, reduce turbulence at tips of an airplane's wing. Decrease thrust, increase turbulence at the tips of an airplane's wing. Okay, so Taranjeet says, I think it's an explanation for the previous one. Negative moment balances the airfoil lift generation at 0 degree angle of attack. No. I'm asking why there is a negative moment. Okay, so it says Cm naught is less than 0. But why is there a negative moment? Why is there a pitch down moment at 0 angle of attack? Try to find out the answer. Next class, we'll discuss this. Okay, now let's get back to this question. What do winglets do? Reduce turbulence at the tips of an airplane's wing. Correct. So what happens usually is that the flow from under the surface of the wing and above the surface of the wing interact at the wingtip, and there are large vortices formed, which in turn gives you a reduction in the lift. This turbulence gives you a reduction in the lift. So yeah, so it's something like this, right? So they interact at the wingtips and it gives you this vortex which travels downwards towards its tail, and it causes a disturbance in the flow, reduction in lift. Okay, so what can be done is that you provide a winglet. What does the winglet do? So this is an aircraft without winglets, and this is an aircraft with winglets, right? So what happens is that the point at which the flow above and below interact is reduced. The area where this interaction happens is reduced. So the vortex is still generated where it meets, but it's a smaller and weaker vortex. Okay, so it gradually, the flow from below the surface and the flow above the surface gradually meet each other, and they happen at a smaller area. So the vortex thus generated is much weaker. Okay, so this was the one without winglets, wingtips. So what happened is that you had large vortices generated. Now, when you introduce this winglets, the interaction of the flow is gradual and the vortices generated are much weaker. Okay, so that is the purpose of winglets. So what does it do? It reduces the turbulence at the tips of an airplane wing. Okay. Determine the tail volume ratio of the vertical tail given that the wing area is 10.35 meters square, span is 10 meters, mean chord is 1.05 meters, vertical tail arm LV is 3.25 meters, and vertical tail area is 1.25 meters. They've asked you to find vertical tail volume ratio, VV. What was the formula? Horizontal tail volume ratio, VH. What was the formula for VH?
STIT by SW into
STLT by S wing into C bar. Okay. Now what would it be for VV, vertical tail volume ratio?
instead of C, it's B.
Exactly. So it will be SVLV by S wing into B. So the reference area in this case is the span. So just quickly substitute all the values and let me know the answer. SV is 10.35. The moment arm is 3.25. 3 area. Okay, that was not, sorry, my bad. This is 1.25. This is 10.35. And wingspan is 10. So what is this answer? What's the value?
0.039.
0.039. That is the right answer. Okay, let's go to the next question. Primary control for spin recovery is, what is spin? What is spin? It's a type of failure, right? So it's some kind of a failure. What happens in that? Can you briefly try to explain? So when the angle of attack goes beyond a certain point, the aircraft stalls, right? So what is spin? So that is one type of failure. Spin is another type of failure. Can you try to tell me what happens there? Okay, Satvik, you said rudder and elevator. Can you explain your answer?
Yeah, suppose a polar plane and anti-clockwise propeller is there, then the plane torque roll on clockwise direction. But we will we will okay, we want a cruise flight like a straight flight. Okay,
Hmm.
that's why we uh, there is a role of elevate sorry rudder and aileron for the cruise fly because the uh, some movement of the rudder like a left side and elevator left side of the aileron is some upward, then the flight opposes the Newton's third law, which is produces there.
Okay. So if it's not a propeller driven aircraft, what if it's a jet engine? What happens then?
Yeah,
Huh.
yeah. Suppose a one engine failure and one engine is working there, but the suppose left side engine is failure and right side engine working, then flight is moving toward the left side. Okay, and also we control that movement of left side. We will upward the aileron of the left side and some tilt the rudder of the left side, which is goes, matlab, it means goes to and opposite Newton's third law like that. I can't explain a better in English. That's why I
Okay,
can't
but
able to
right
explain.
now you mentioned ailerons also, right? But you said only rudder and elevator. So if one
Sorry,
engine,
not rudder and aileron. Sorry, not elevator. That's a aileron.
okay, okay. So that is his answer. Does everybody agree with it, or does anybody have a different answer? Before all of that, what is spin? Can someone try to tell me what spin is? So the two conditions that he mentioned was that if it's a propeller driven aircraft, if it's rotating in clockwise direction, there is a induced roll, and if one engine fails, for a jet engine case, if one of the engines fails, then there is again a roll and a yaw introduced, right? But a spin happens even if these conditions don't occur. So even if it's a jet engine with both engines working perfectly fine, spin occurs. Why does it occur? Okay, yaw-like motion. Okay, yes. So what happens is that both for spin to occur, it moves in a when the spin occurs, the aircraft moves in a helical downward spiral, right? So that's what spin is, right? Why does it happen? Yes, so it's a yaw aggravated stall. What happens is both the wings are stalled. For spin to happen, both the wings must be stalled. But one wing should be stalled greater. So it should be at a greater angle of attack than the other wing. What happens is that, so for example, if the right wing is alpha greater than alpha stall, left wing is also alpha greater than alpha stall. And if the right wing's angle of attack is more than the left wing's angle of attack, both of them more than the stall angles of attack, the right wing produces lower lift, right, than the left wing. And so right wing will be in the inside edge of the spiral and it will continue downward that spiral. It will continue along that direction until you do something for recovery. So let me try to explain using the slide. Yeah.
Can you show this with any video or picture?
Yeah. So I
Yeah,
have,
picture able there, but some videos because can't recognize with only a picture.
okay, I think you can Google a spin so you'll be able to know what happens. But I think this picture should suffice. Okay, so
Yeah,
what,
okay,
yeah,
problem.
I'll just try to explain it. Or you can try to get some videos, or in the next class, I'll come up with some video. But let's just try to go over this, okay? Okay, so both the wings are stalled. right? But one wing is more deeply stalled than the other. And the wing that is more deeply stalled is on the inside of the spin. So this wing, this side of the wing is more deeply stalled, and the lift produced on that wing is much less than the lift produced on the other wing. So this is the lift on this wing, and this is the lift on the outside wing, right? So it tends to dip towards the inside, right? It tends to dip and it follows that path, and progressively the lift is reducing on both the wings. So it moves downwards. How does it move downwards? In a spiral. And the spiral, the inside of the spiral is the wing that is more stalled, or the wing that produces less lift. Okay. And the protocol to follow for spin recovery is PARE. That is how you remember it. So first you're supposed to set the power to idle. So take off all the power to the aircraft. Then set your ailerons to neutral, right? And then you put your rudder in the complete opposite direction. So when they say primary control surface to recover from spin, it's this. This is mandatory. You have to put your rudder to the complete opposite direction. Why do you have to make your ailerons neutral? After you make your rudders complete opposite, you recover from the spin, you need to ensure that your wings are producing the same lift, or it may tend to go back into your spin, right? So you need to make your ailerons neutral. Similarly, when your rudder is deflected completely in the opposite direction and comes back, your alphas on both the wings should not be stalled. So alpha should be less than alpha stall, and hence the elevator must be adjusted to reduce the angle of attack. So this is the process that is followed. So first you set your power to idle, take off the power, set your ailerons to neutral, set your rudder in the completely opposite direction, and make the elevator deflect such that the angle of attack is reduced. Okay, so this is the sequence that you follow. But the primary control surface, primarily what takes care of the spin is rudder. I hope the spin, what spin is clear now, but I will try to come up with a video in the next class. Okay. Okay. So let's move on. Why dorsal fins are used? What are dorsal fins? To improve tail effectiveness, to reduce tail effectiveness, similar to horizontal tail, attached to rudder. Okay, so let me try to understand that. Excuse my poor drawing, but right. So this is the rudder, right? This is rudder. So where in this figure do you think should the dorsal fin be? When you say attached to rudder, I'm just trying to understand where you meant. In front lower of the rudder. So you mean somewhere here? Root of the tail. Yes. So it's, I think what he meant was like in front of the tail, not the rudder. Rudder is the movable part, right? Rudder is the control surface on the vertical tail. Dorsal fin is this part. So one extra angle. It is part of the vertical tail, but at a different sweep back angle, right? So that is the dorsal fin. Okay, correct. Yes, so that is what you meant, correct. So why are these dorsal fins used? So this is the dorsal fin, right? So this is the dorsal fin. So why are they used? I think I have, yes. So these are two similar aircrafts. The one above has a dorsal fin, this portion of the vertical tail, which is swept at a different angle. This has a linear slope, right? So this has varying slopes, correct? So the first aircraft, the one above, has a dorsal fin. The second aircraft, which is very similar, does not have a dorsal fin. So why is this dorsal fin used? So these aircrafts are the 737 and the A320. So why is this dorsal fin used? Controls lateral stability. Okay, yes. So it's from these options, what do you think is the right answer? To improve tail effectiveness at high side slip conditions, right? It's right, to improve, yes, directional stability at high angles of side slip, correct. So that is the right answer. So when this high side slip conditions occur? So in the previous question, somebody had said that when the engines fail. So such conditions, one condition where high side slip occurs is the crosswind, right? Another thing is when one of the engines fail, then also you encounter high side slip situations. Okay, so what happens is that the vertical stabilizer, the vertical tail, ensures vertical tail with the dorsal fin gives you wide range of side slip angles to operate on, right? So because of this introduced change in the slope, so the dorsal fin gives you change in the slope of the vertical tail. It ensures that you're able to operate for a wider range of side slip angles, right? Because it increases the wetted surface area and you have more control for a larger range of side slip angles. All right. So the correct answer is it improves the tail effectiveness at high side slip angle conditions. And when do such side slip angle is beta? When do such conditions occur? One is crosswind and one is when one of the engines fail, right? Okay. Okay. Next question, find the degree of elevator float. Consider tail angle of attack is 2 degrees. CH delta E is minus 0.005 and CH alpha tail is minus 0.0052. What is elevator float? Okay, before that, what is the CH delta E and CH alpha T? What is the CH? So CH delta E is D CH by D delta E. Delta E is elevator deflection. What is CH? Similarly, your CH alpha tail is DCH by D alpha tail, which is alpha T is the angle of attack witnessed at the tail. Delta E is the elevator deflection. What is CH? What is CH? So it's the hinge moment coefficient, right? I hope you've all done the stability control course. It's the hinge moment coefficient. What is the hinge moment? So if this is your tail, and this is your elevator, right? This is the hinge point about which the elevator is deflected. So the moment at that point, at that hinge, is hinge moment coefficient. Okay, so moment at that point is the hinge moment. Okay, and the coefficient, the non-dimensional parameter is CH, coefficient of hinge moment. Okay, okay. So now what is elevator float? What is elevator float?
Elevator, the use of elevator is to upward and downward flow of the airplane.
Yes. That's true. But what does it mean when I say elevator float? Okay, so elevator is deflected upward and downward by giving some control of the pilot gives some control, right? So when the pilot lets go of this control and the elevator is allowed to freely float, that angle is elevator float, right? So the effective moment at the hinge will be 0, correct? So now let's write down the equation for hinge moment. Coefficient of hinge moment is, it should have a CH naught, but since we use symmetrical airfoils, the CH naught usually goes to 0, okay? Plus CH delta E into delta E plus CH alpha tail into alpha tail, okay? So now from this equation, can you tell me how do you find out elevator float? It's the point where the elevator is allowed to freely float. That means your hinge moment becomes 0, right? So it will be 0 equals CH delta E float plus CH alpha tail into alpha tail. So can you tell me what delta E float is from this equation? You have all the data, you just have to find out delta E float. Just substitute the values and let me know what delta E float is. Minus CH alpha tail by CH delta E into alpha tail. What is the value? You have all of these quantities. Minus 2.08. Okay, so it's minus 2.08. Correct. So that is the right answer. Okay, so these are the formula that we used. Hinge moment is given by this, similar to your pitching moment coefficient. Then the hinge moment coefficients formula is this. So CH naught is usually 0 because you use a symmetrical airfoil for your tail. CH alpha tail into alpha tail, CH delta into delta E. What is this delta T? What is delta T? Delta E was elevated deflection. Alpha T is angle of attack at tail. What is this delta T?
Deflection of tail.
How do you deflect your tail? You can't deflect the tail, right? The tail is fixed. You can only
Not the
deflect.
tail, not the deflect the tail. Actually, we deflect a rudder or elevator.
So the rudder is not on the tail, it's on the vertical tail. This is all related to the horizontal tail. Deflection of elevator is given by delta E. This is deflection of elevator. Deflection of elevator. Okay. So what is delta T? So delta T is the deflection of the trim tabs. So your tail is something like this. And this is your elevator. And that's the hinge point. And it has another surface, trim tabs, right? That is further beyond the elevator. Trim tabs. So the deflection of this trim tab is delta T, okay? So since that parameter was not given in the question, we assumed it to be 0, okay? Okay. Go on to the next question. Hinge moment coefficient depends upon. We just saw the equation for hinge moment. What does it depend upon? This is the formula. Hinge moment coefficient depends upon. We just saw the formula. So it's this one, right? So tail angle of attack, elevated deflection, correct. So first one is the right answer. Hinge moment coefficient depends upon tail angle of attack, elevated deflection, deflection of trim tab, etc. Okay. Yeah, so these are the same formula that we saw in the previous slide. What is the aspect ratio of a wing which span 11 meter and chord 0.62 meter? Assume rectangular wing. This should be very simple. I've asked you aspect ratio. Formula for aspect ratio is B square by S. Now tell me the value. 17.74. I'm not sure what the answer. Let's just try doing this. So it's for a rectangular wing. So B into V by what is the area? B into C. So that is 11 square by 11 into 0.62. 11 by 0.62 is 17.74. Correct? I hope this is clear. It's fairly simple. Yes. Okay. Now that we have some time, let's just discuss a new concept. How do you calculate aerodynamic center? Okay, so these are a few empirical formulae that we will use to calculate the aerodynamic center. The first one, aspect ratio, we know, B square by S. The other thing is taper ratio. Lambda is CT by CR, where CT is the chord at the tip. So this is CT. This value, the length of the chord at the tip. Length of the chord at the root is CR. This quantity is CR. Okay. And C bar, which is denoted here, is the mean aerodynamic chord. Okay. Not the chord at the tip, not the chord at the root. The chord at the mean aerodynamic chord. Okay. Which is what we use for our calculations. So what we have to find out is the aerodynamic center. So aerodynamic center is somewhere, let's say here. So we need to find out the X and Y coordinates of the aerodynamic center. Now, Y coordinate of the mean aerodynamic chord is given by this formula, right? So that is an empirical relationship. We can directly calculate this. And C bar, similarly, the length of the mean aerodynamic chord is given by this empirical formula. But we also need to find out X, right? So we need to find out X, and the reference point is the leading edge. So this is XMAC. Okay, so we'll just do a question and see how to calculate this with actual values. Let's just try doing it. Okay, so this is what is given to you. They've given you root chord. So this is CR. They've given you taper ratio. Okay, before that, so they've given you taper ratio as CT by CR. So if it's a rectangular wing, what will the ratio be? Taper ratio for rectangular wing. What will it be? One, correct. What if it's a triangular wing? What will it be for a triangular wing? 0, correct. So C bar for a rectangular wing, what will it be? Using this formula. Taper ratio you have just found out. So what will the C bar, mean aerodynamic chord, length of the mean aerodynamic chord for a rectangular wing, what will it be? It will be CR, correct. And C bar for triangular. C bar for triangular, what will it be? Two by 3 CR, correct. Okay, so now let's move on to the question. Okay, so they've given you root chord 1 meter. CR is 1 meter. Taper ratio is 0. So what type of wing is it? What is the shape of the wing?
Triangle.
Triangle. Yes, so it's a triangular wing. And the half span is 0.5 meters. So this is B by 2 is 0.5 meter. And they've said taper axis is mid chord. Okay, so what does it mean? Taper axis is mid chord means, so if this is your root chord and here tip chord is 0. So this, so it's tapering about the mid chord. Okay, if I had said taper axis is trailing edge, how will the shape of the wing be? It will taper towards the trailing edge, right? So it will look something like this. This taper axis is mid chord, and this taper axis is trailing edge. Now, if the taper axis was leading edge, it would be something like this, correct? You can have other taper axis, for instance, taper axis is quarter chord point. So then it would be, if this is your quarter chord, it would be something like this, right? So these are different shapes, and according to the taper axis, you can have different types of triangular wings. These are all triangular wing shapes, but the taper axes are different for each of them. So in our case, this is the shape that we're dealing with. Taper axis is mid chord. Now they've asked us to find aerodynamic center. So we need to find out XAC, YAC, and we have to find out aspect ratio. Okay. Okay. Let's try doing this. Yeah. So this is the wing section, and these are the formulae. These are what is given. Yes. Okay. So now let's try finding out the XAC, YAC, C bar. Okay. Now, if this, so on the mean aerodynamic chord, at what point will the aerodynamic center be? So if this is your AC, let's just draw this line and draw this line. What is this distance? So aerodynamic.
C by 4.
Exactly. So it's C bar by 4. So quarter chord point is the aerodynamic center. This is your AC. Okay. So we need to find out YAC, XAC. So let's start with finding C bar. So what will the value here be? 2 by 3. CR is 1 and taper ratio is 0. So it's just this. Okay. It's clear, right? Taper ratio is 0 because it's a triangular wing. It's given in the question. Okay. So this value is just 2 by 3 and CR is 1. So it is 0.667. What about YMAC? Location Y coordinate of the mean aerodynamic chord is B by 6 and the taper ratio is 0, which is B by 6. B is 1 by 6. How much is this value? 0.3, 0.1667, right? So we have found out YMAC. Now we need to find out XMAC. How do we find out XMAC? XMAC is this quantity. This is XAC. What is XAC? XAC or XMAC? How do you find out that length? This small length, let me just try using a different color. What we need to find out is the one in red. So the green, oops. Let me just erase this. Now this is your AC. Okay. So this distance is C bar by 4. What we need to find out is this length in green, right? So green is XAC, which is what we need to find out, right? How do you find out, XAC? What is that length in green? How do you find out XAC? So it is this length in orange plus C bar by 4. Is that correct? Yes? So green length is orange length plus red length. Clear? Okay, so XAC is the orange length or the red length. So C bar by 4 plus the length in orange. What is the length in orange? Can you try to tell me? What is the length in orange? So I will write it. Just tell me if it's correct, if it makes sense to you or not. Okay. CR by 2 minus C bar by 2. Tell me if this makes sense. Is this right? Yes, okay, it's clear to everyone. Why XAC is C bar by 4 plus CR by 2 minus C bar by 2. So the length in orange is CR by 2 minus C bar by 2. Okay, so you can find out XAC that way. Let's try to find out the value. So C bar by 4 is 0.667 by 4 plus CR by 2. CR is 1. 1 by 2 minus 0.667 by 2. What is this value? Just simplify it and tell me.
0.1665.
Is it? Just try doing it again. I'm getting 0.3. Just try doing it again.
Yeah, the x value is 0.16. If we add C by 4, we'll get the total here.
So what is this XMAC? What is it's 0.3, right?
Yeah.
Yeah, okay. So it's 0.333 meters. Okay, so this is your, they've asked you to find out aerodynamic center. So it's YAC and XAC. Next, what do they ask you to find out? Aspect ratio. What is the aspect ratio? Is B square by S. Span is 1 square by S. What is the area of the wing? What is the span? How do you find out? Just find the area of one triangle, multiply it by 2, right? So 2 into, what is the area of one triangle? This area. Half base into altitude. So half, what is the area? Half into CR into B by 2, correct? So it would be 1 by 2, CR is 1, B by 2 is 0.5. What is this value? 2, right? So aspect ratio is 2. Correct? Is this calculation of the aerodynamic center and the aspect ratio clear to everyone? We'll try doing another question now, but is this clear? Okay, let's move on to a different question. So here they've given you root chord. CR is 0.9 meters. Tip chord. CT is 0.15 meters. So here it's not a triangular wing, right? Because your CR and CT. CT is 0 for a triangular wing. Here they've given you CT. So it's not a triangular wing. Span is 1.75 meters. Taper axis is the trailing edge. you need to find out AC, aspect ratio, and leading edge sweep angle. So what would the shape of this wing be? So this is your root chord, and it says it's tapering about the trailing edge. So it needs to come down. So it will be a sweep back, right? And you have root chord and tip chord. So this is, say, your tip chord, and this is the shape of your wing, where this is CT, this is CR, your mean aerodynamic chord is somewhere here. So this is C bar, and this is your AC. Okay. Can you try to find out AC, XAC, YAC? So I'll just get to this. So this is the shape of the wing, right? And these are the formulae. Can you try to find out just the aerodynamic center, XAC, YAC? Can you find those values? Just try doing it by yourself, and then we'll do it together. Okay. This, I believe, is simpler than the previous case. So let's try doing this. C bar and YMAC, you can directly find out. Try to find out XAC. I'll just draw that again. So your aerodynamic center is somewhere here. This value is C bar by 4. And okay, let me take another color. This is XAC. That's what we need to find out. Okay. Yes. Let's try doing this, and then we'll do it together. Just take a few minutes. Okay, XAC is still C bar by 4 plus the length in orange. How do you find out the length in orange? Just try doing it. It's simpler than the previous case. You can try doing this. Just take a few minutes and try doing it, and then we'll do it together. Okay, so what is the distance in orange? Can someone tell me? What is the value? What is the distance in orange? In the previous case, it was? Yeah, so in this case, it was CR by 2 minus C bar by 2. Okay, so similarly, what is it in this case? What is the distance in orange? XAC is 0.2965. Okay, but can you tell me what is the distance in orange? How did you get XAC is this value? C bar by 4 plus what is the quantity in orange? How did you get this value? You can't use the same formula that changes from shape to shape, right? Which is why I told you to do this. So this distance in orange will not be CR by 2 plus, it will not be the same thing. It will be different, right? Can someone tell me what the distance in orange is? What is this distance? It's very simple, right? You can get it from geometry. So let's just try doing this. This entire thing is CR. This distance is C bar. So what is this? It's just CR minus C bar, right? Is that clear? The distance in orange is just CR minus C bar. Yes? Now can you try and find out? Now it should be fairly straightforward, right? So C bar is 2 by 3. Oh, before that taper ratio, CR by CT, that is root chord is 0.9 by 0.15. That is the taper ratio. What is the value? Taper ratio, what is the formula? CT by CR. My bad. Let me just erase this. Oops. So it is CT by CR, that is 0.15 by 0.9. What is this value? 0.166. Is it? Okay. Just substitute the values and tell me what is C bar. One plus 0.167 plus 0.166. 0.167. 0.6143. Okay. 0.6143. Okay, what is YMAC? B by 6. B is 1.75 by 6. 1 plus 2 into 0.1667. 1.17. What is YMAC? 0.33. Okay. And this XAC? 0.45, right? Do correct me if I'm going wrong somewhere, but I think it's 0.45. Okay. So this is the AC. Next, they've asked you to find out aspect ratio. Aspect ratio is B square by S. So B square is 1.75 square. What is S? How do you find out S? How do you find out the area? So you split the shape into two shapes. I find it easy to do it this way. So I take one rectangle and then the triangle. Right? So first area of the rectangle will be span into CT. And area of the triangle will be, what will the area of the triangle be? Half. Base is span into height is CR minus CT. Correct? So what is the aspect ratio? Can you tell me the aspect ratio? Just calculate this. The formula is given there. So how do you find out the area? You split your shape into simpler shapes. Okay, so I find it easy to make it a rectangle and triangle. So area of the rectangle is the span into CT. Area of the triangle is half base into altitude. And the value is, aspect ratio value is 40.16. What is the value of aspect ratio? Just substitute the values and tell me. Is it 7.7? Try doing it again. .33, correct. So this is the right answer, 3.33. Then they've asked you to find out the sweep angle. So they've asked you to find out the leading edge sweep angle, right? So how do you find out that? This is the leading edge sweep angle. How do you find that? So tan of that angle, tan leading edge sweep angle, what is the value? So it's CR minus CT. It's only for this case, okay? It's only for this case, CR minus CT by B by 2, opposite by adjacent. So if I draw a triangle here, this length is B by 2 and this is CR minus CT, correct? So sweep would be tan inverse CR minus CT by B by 2. What is this value? .6 degrees, yes. So is this clear to everyone how to find out aerodynamic center and other geometric parameters when some parameters are given to you? I hope this is clear. Over the course of the next few weeks, we'll try doing some other examples so that it becomes thorough. But I hope these two examples are clear. So I think with that, we come to the end of this week. If anybody has any questions, please do ask me. If not, we'll end the session here. Okay, if nobody has any questions, we'll end the session here. Thank you very much. We'll meet again next Tuesday. Okay, Taranjit, did you have a question? What is delta T? Where is delta T here? Oh, you meant in the previous thing? It was trim tab deflection. So where was it? Yeah, so it was the deflection of the trim tab. Trim tab deflection. Okay. Any other questions? Okay. If not, we'll end the session here. We'll meet again next Tuesday. All the very best for your assignment. Thank you.